Now let's consider the Denso arm. This is an arm that's of industrial use, but also is used in many educational labs. This is a nice sketch drawing of the arm where there's a base rotational degree of freedom here, a rotational degree of freedom here, rotational here, and then maybe two more at the wrist. So when we draw this robot in the schematic form, we have this rotational degree of freedom that's vertical, joint 1. Joint 2 and joint 3 are axes that come out of the projector. Joint 4 is horizontal. Joint 5, again, out of the projector screen. And then joint 6. These last 3 degrees of freedom constitute the wrists. These first degrees of freedom are the base of the robot. Now, when we do the Denevit-Hartenberg transformations for this particular robot, we're going to choose a different reference configuration. The reason why we chose this reference configuration is it looked like the robot. But it would be more convenient to choose this reference configuration, where we have just our rotational degree of freedom vertically pointing up, and then we have this fixed 90-degree rotation here, and now the next 2 axes are out of the whiteboard, and then here's your wrists. Noted here are the distances between between the degrees of freedom, and what we did is we can redraw this frame here in 3 dimensions so you can see how the z and x axes are being assigned. And notice that frames 0, 3, and 5 don't coincide with their joints. In other words, their origins aren't physically located at a point on a rigid body on the robot, which again we agree is okay because all we care about is the motion. With the frames assigned, then it's a rather straightforward exercise to go through each of these rows one at a time to figure out the transformation from frame 0 to frame 1, from frame 1 to frame 2, and so forth. So here, let's look from frame 0 to frame 1. So our z-axes, we have a z-axis here and a z-axis coming out of the whiteboard. The link length, the distance between those z-axes, is 75. And when we do our right-hand rule, z0, z1, we'll see that we're pointing in the opposite direction that we have labeled for x1. So this gives it a negative 90 degrees for the twist. And of course, the joint variable is theta 1. Now, when we go from frame 1 to frame 2, that's this row over here, the z-axes are indeed parallel to each other. Of course, this gives us plenty of choices for where our x2 axis should be, but we choose the x2 axis such that the offset is going to be 0. The distance between the z-axes, the link length, is 270, and then once again, our rotational degree of freedom is theta 2. Now let's look at row 3. This is the transformation from frame 2 to frame 3, which we've chosen over there. Once again, our z-axis, we have a z-axis coming out of the board, and we have a z-axis that's perpendicular. So the distance between those axes is 90. That's the link length. z2 comes out of the board and down. So we're pointing this way, which is the opposite direction of x3. So that gives us a negative 90 degrees. And then once again, we have our theta 3 for our joint variable. So now let's look at row 4. This is the transformation from frame 3 to frame 4. So we have a z-axis here and a z-axis coming out of the board. These z-axes intersect, so their link length naturally is going to be 0. When we look at how they intersect, z3 goes down and z4 comes out, thumb pointing this way, which is collinear with x4. It points in the same direction as x4, so that gives us a positive 90 degrees. And the distance between our x-axes is 295, so our offset is 295. Now, when we go from frame 4 to frame 5, you'll notice that they share a common origin. So immediately, our offset and link length are going to be 0. We know our rotational degree of freedom is theta 5, so the only thing left is to figure out what's the twist. So from z4 to z5, z4 is coming out, we go down, we're going out, we go down, we're pointing this way. That's the opposite direction for what we labeled as x5, so that gives us a negative 90 degrees for the twist. Now, to go from frame 5 to frame 6, this is the last row of the Denford-Hartenberg transformations. We notice that, once again, Z5 and Z6 are collinear, so that means that the link length and twist are both going to be 0, and the distance between the x-axes by this convention is labeled as 80, and of course theta 6 is the rotational degree of freedom. So here we have the Stanford arm. It is a 6 degree of freedom robot, rotation degree of freedom, rotational degree of freedom, prismatic joint, and then a 3 degree of freedom wrists. This example, again, we have our z-axis pointing up, z-axis horizontal, z-axis pointing up, z-axis pointing up, z-axis horizontal, and then z-axis pointing up. This is the resulting table, and I'm going to do this a little bit differently than before. Instead of going row by row, let's see if we can get away with doing this by the columns. So the first column is pretty easy. Since this is an RRPRR robot, our joint angles are all going to be this theta 1 through theta 6, with the exception of theta 3 star. We know at this reference configuration, these numbers are all 0, so we don't have to worry about adding any additional numbers there. The link lengths, this is interesting. They're all going to be 0 here. That makes sense. These two axes intersect. These two axes intersect. These axes are collinear. Last 3 axes all intersect. So that makes these link lengths all 0. So the real hard part here is figuring out where the x-axes are so we can figure out what the offset parameters are indeed. Now the 3rd degree of freedom, that's pretty easy. That's just this d star over here. Maybe we should call it d3 star, but d star is fine. That's straightforward. So now let's work our way up. So now let's see if we can just do the offsets by inspection. So from this frame to this frame, we can either pretend that they coincide, which I don't think is a good idea because I don't think we have a 2 degree of freedom joint over here in the Stanford arm. We're missing a D1, distance from here to here, so maybe this is a mistake in the table. This should be a D1. And then from here to here, this distance, the distance between the x-axes, that's the D2. The last 3 offsets we actually covered when we discussed the Euler wrist earlier. So that's it. These examples are starting to become easier and quicker to do. So now let's do the SCARA arm. The SCARA arm, when viewed from above, is like a 3 degree of freedom planar robot. Here is a vertical axis, another vertical rotational axis, and another vertical rotational axis. If we were to look from above, these would look like circles with dots in the middle. But we're looking at it from the side because we want to emphasize there's this prismatic joint over here. So we have a rotational joint around this axis, a rotational joint around this axis, a prismatic joint, and then finally a prismatic joint around this axis here. This is a 4 degree of freedom robot which was designed to be able to rapidly insert items, say into a tray in an automation system. We don't need the full 6 degrees of freedom. We were able to save money by having 2 fewer degrees of freedom, and it's more robust, more rigid in this linear last degree of freedom. So by inspection, it's pretty easy to see that our variables are theta 1 star, theta 2 star, d3 star, and theta 4 star. Theta 1, theta 2, d3, theta 4. The link lengths also are fairly easy to see. The distance between this z-axis and this z-axis is a1. Again, if we were looking from above, it would look like a 2-link robot, a1. The distance from this axis to this axis, that's the a2. So that's a1 and a2. And then for the remainder, all of the z-axes are aligned, so our twists and offsets are also going to be 0. The only thing left is this d4. And this d4 tells us the distance from this last rotational degree of freedom to the end effector.